CLIQUE, it's different from all the other ones that we have talked about, but it also brings us back some old memories. CLIQUE is a bottom-up algorithm. It divides your dimensions into sub-spaces. It actually uses Apriori Principle again to efficiently prune potential clustering. So the idea why CLIQUE is developed, we know that clustering in high-dimensional data space is challenging, but maybe meaningful clusters exist already in some of the subspaces. Maybe we don't need to consider all the dimensions. Even in our police shooting data, we can see maybe we really don't need all of those 12 parameters. If we actually narrow it down, we're probably going to find meaningful clusters. So CLIQUE is the first dimension growth subspace clustering algorithm. The idea is let's divide our spaces, our dimensions into intervals. Every dimension is divided into intervals. So we can see we create a grid that way. Then we start, it's a bottom-up approach. We start at single-dimensional subspace. And then we try to combine dimensions to grow into multi-dimensional subspaces. Along the way, we see which subspaces is actually dense. If a subspace is not dense, we can just forget about it. We will just mark it as maybe noise or outliers. Yeah, this is a few graphs that I copied from the original paper. You can see your data in high-dimensional space could be with a very complex structure. It will be very challenging for any algorithm to cluster exactly those combinations of things and have different twists and turns and find them perfectly. However, if you actually present the data in lower dimension, this is only one-dimensional with the index of the data. You could also project it into two-dimensional data where you can see there's very clear clusters and mixed things. If you actually divided the task into lower dimensions, you can actually, in dimension A and B, you can find two clear clusters, and in dimension B and C, you can find another two clear clusters. So that's the idea of CLIQUE. So the intuition, I think I already said it. I think I did, but let's just clarify some of the terms that we're going to see in the next slides. So once we divided those data space into intervals and created subspaces, then the CLIQUE clustering algorithm identifies the sparse and the crowded areas. The crowded areas are called dense area, and those subspaces are called units. And then by connecting those units are dense if the total data points contained projected into this unit exceeds a parameter, a threshold. Again, user have to provide threshold. And then a cluster is defined as a maximal set of connected dense unit. I think so there are conceptually three major steps. One is division, partition. Each dimension is partitioned into a number of intervals. This m-dimensional namespace then is divided into non-overlapping rectangular units. And then for every unit, we can define, I didn't count how many data points are in there, When we have lots of units, that can be very challenging, time-consuming. But here, because we're growing from bottom up, we can apply a priori principle to help us. I have examples in the following slides to show that how a priori principle can be used. And once we identify the dense unit, the last task is just to connect those dense unit and form clusters. So a unit may be a rectangular space. So each interval defined by these two different dimensions would form this rectangular unit. If the data points, number of data points within this unit exceeds the threshold, then this is dense. This is obvious sparse, it's empty. This is dense. Clustering is just when this dense area has other neighboring dense areas, we will just connect them to form clusters. So data points are multidimensional, but they are projected into subspaces. Even if you have three-dimensional data, we can project it into two-dimensional space and count. So I have examples later to show that. So to review what a priori principle was, I think this is the third time we see it. When we apply a priori principles here, the idea still is very intuitive. If a k-dimensional unit is dense, then all its projections into lower dimensions has to be dense. Does that make sense?
Yeah, it makes sense.
Yeah, good. Yeah, because if those 3 points are clustered in those three-dimensional space, projected into any of the two-dimensional space, you still have that 3 points. The points won't get reduced, right? So if a k-dimensional unit is dense, then all its projections into lower dimensional space has to be dense. Given a k-dimensional candidate unit, dense unit, if any of its k-1 projection unit is not dense, then this k-dimensional unit cannot be dense. Same idea, we're just saying it in a different way. So then again, we apply this a priori principle that we can start with one-dimensional and then grow. We don't like to read words. Okay, so this is my example. Let's see, we have three-dimensional space data, age, vacation, and the salary. Those data are distributed in the space look like this. If we project those data into two-dimensional space, so this one only have age and salary. So if we project those, if we shoot a light from top down, we will see the shadows of those points on this two-dimensional space, and that's going to look like this. It may not exactly look like this because I just for illustration purpose, I put dots there. It may not corresponding exactly to what we get here, but you get the idea. For vacation and age, again, we could do vacation and age if we shone a flashlight from this direction. From this direction, the shadow is going to be projected onto vacation and age dimension. So let's see, we have this as a dense. So if we see that the number of points in this unit is greater than 2, then this is considered a dense. Then we have a dense unit here. We have a dense unit here, and all those units are dense. But we will first work on this unit that was pointed at with a blue arrow. We have a dense unit C1 and dense unit C2. So dense unit C1 was age 20 to 30, vacation 1 to 2 weeks. And the other is this age range and make this much salary. So then in order to decide whether C and C1, C2 can form a dense cluster, we first check those two things are mergeable, they're joinable. all but one dimension is different, right? So that's exactly the same thing that we did when we do association rule mining. They are joinable, so we created a candidate unit, C. Now we need to decide whether C is dense. So to form this C, we need 3 dimensions, and we already know these 2 projections are dense. So we need to figure out whether the 3rd projection is also dense. If it is not dense, then we don't need to consider C at all. The C cannot be dense. If it is dense, then we need to count how many points in C there actually is to decide whether it's dense or not. So from bottom up, recursively, we can merge, find denser, higher dimensional spaces. This is how CLIQUE finds clusters in subspace. So the strength, it's quite, well, I mean, for the first person to think of this idea, I think that was very, very smart. So it automatically finds subspaces where the data clusters. It's insensitive to the order of the record. How you input it doesn't really matter, right? It does not require any prior knowledge of data distribution, just count how many points there is. It actually scales very well using Apriori Principle. And it can find overlapping clusters. This may be a strength. It could also be a weakness if lots of things are just clustered, overlapping. It's very hard to read, and it's getting hard to understand. So the weakness, we set 1 global density threshold and the grid size for the entire data set. This obviously going to limit, make the algorithm more rigid than what we would like it to be. Okay, so that's the last slides I have. I have made a R exercise using CLIQUE because I thought it was interesting. I want to see what's inside the subspace clusters. So let's have a quick summary. I think we emphasized this, but I think it's worth to emphasize again. For clustering algorithm, because it's unsupervised, there is not a gold standard for you to check your result to. Clusters can be found in random and uniform data. See, if you use k-means on this random set of points, you find 3 clusters. You use dbScan density based, you still have clusters. Okay. Even random data, I am sorry. Any random uniform data produce clusters. So you definitely need our methods to determine clustering density. I am sorry, this is my freelancer developer. Sorry about this. Comparing. So we said when we're doing the first class on cluster, we say there is not a gold standard for you to validate the result of your cluster analysis. So there's multiple ways to do that. You probably want to use more than one way to validate your result. So when you have external class labels, you can use that. Sorry, guys. You can also, if there's a gold standard, we have this B cubed position recall measurements that you can use to compare your result to gold standard. But a lot of times you don't. So you have to use only the data and see whether the clustering actually makes sense. You could also compare results of 2 different cluster analyses to see which makes better sense, to see what issues, why they're different. Those questions can often help you to identify issues or add to your confidence that one cluster is better than another. And some clustering algorithms ask you to provide number of clusters as parameters, like k-mean and PAM. And we have introduced a number of methods to help you to do that. So again, there is not a prescribed procedure that can show you that your cluster analysis is definitely good. And it's with any data analysis tasks, multiple evidence verification and understanding the problem are going to be helpful. On the last slides, I listed some of the algorithms that we studied. You can add a few more that I missed that summarize what we have learned so far, the algorithm, what kind of data it works on, the shape, what are the input parameters, limits, and the strength. That may be useful. I think it's going to be at least useful for one of your homework questions. Questions?
So for CLIQUE, the last one that we have, what are like the weaknesses in that? It sounds like it is quite a like I see what you say here. The accuracy may be degraded because of simplicity, but like I was trying to think of when we might use CLIQUE versus say dbScan or some of the other methods. So could you help us understand that?
I think it's going to be helpful if we look at my demonstration. I think the result is not that intuitive. When especially when you have large data set. I'm going to do a little demo now with CLIQUE. It finds lots of clusters in lower dimensions. It does not give you an entire clear picture how your data may be grouped into, like it's not visually direct that you have this many clusters.